Hey there everybody, and welcome to a brief video on section 18.4. This is about normal subgroups and factor groups. I want to define these two terms for you, and that will finish out chapter 18. So here's the basic idea. Suppose you have a group, like say Z8 under addition, and you want to impose this condition. You say, I think 4 should behave like 0 now. Well, if you do that, then now 5 would have to be 1, like this follows logically as a consequence, because 5 is 4 plus 1. 6 would have to be 2, and 3 would have to be 7. And as a result, you've now taken your original group and carved it up like this. You've now said like 0 and 4 are the same, 1 and 5 are the same, and so on. And then uncoincidentally, these are the 4 cosets of the subgroup consisting of 0 and 4. Okay, so once you've carved your group into these cosets, 0, 4, 1, 5, and so on, if you want to get a group structure out of that, if you want to say like, oh, I got 4 things right here now. 4 things because like 0 and 4 used to be different, but now they're the same. So 0 and 4 is a thing, 1 and 5 is a thing. If I want to define addition on those sets, it seems like the most natural thing to do would be like, all right, well, if I want to do set plus set, I should just form all possible sums I can. So like 0 plus 1, 0 plus 5, 4 plus 1, 4 plus 5. And if you form all such sums, you just get the set 1, 5 back. Because 4 plus 5 is 9, but that's 1 in Z8. So 0 plus 1 is 1, 0 plus 5 is 5. 4 plus 1 is 5, 4 plus 5 is 1. So if you do all possible sums of these two sets, then you just get back the set 1, 5. And similarly, if I wanted to add the set 1, 5 to the set 2, 6, like what would that even mean? I could again do all possible sums. 1 plus 2 is 3. 1 plus 6 is 7. 5 plus 2 is 7. 5 plus 6 is 11, but in Z8 that's 3. So you can define addition on these sets if you want to, and if you build a Cayley table or play around with this a little more, you can quickly convince yourself that even though I've written my group elements as sets consisting of 2 objects, kind of clunky notation, right? I've really just formed the group Z4. That's all I've done. If you start with Z8 and then you insist that 4 is 0 now, then you've just made Z4. That's all you've done. You now basically just have a group consisting of 0, 1, 2, and 3 under regular addition. And since 4 is 0, like 3 plus 1 would be 4, which is 0 now. And so what this set notation is keeping track of is just like what elements got glued together as a consequence of you gluing together 0 and 4. If you glue together 0 and 4, in the end, you get a coset structure, which is basically just the group Z4. So that's the idea of a factor group. Z4 is a factor group because you can obtain Z4 from Z8 via cosets like this by gluing different elements together. So that's the idea of a factor group. That's the point of this section. So it turns out that if you want to create group structures out of cosets, you can't just start with any kind of subgroup. So the subgroup you start with has to have a certain kind of property, and it has its own name called normal. If a subgroup is normal, then this thing I just did, where you can like kind of combine subsets via the original group operation, that thing works out and works nicely if your subgroup has a particular property. So that's what I'll define for you now. So a subgroup is called normal if its left cosets and its right cosets are the same. So if GH and HG are always the same, if those are the same sets, they contain the same elements. And just a quick note, if your group is abelian, then all subgroups are normal because you can just flip the multiplication, just write G on the left if you want to. Another way of thinking about normal, it's not obvious, by the way, these definitions are equivalent, but I throw it out here because we might use this later. The subgroup H is normal if for every group element in the overall group, doesn't have to be in the subgroup, and every subgroup element, if you form this triple product, G times H times G inverse, you don't leave H, don't leave capital H. And this makes some sense because if you look at this equation here, imagine multiplying this equation on the right by G inverse. If you did that, this G right here disappears, and there's a G inverse right here now, and you're saying G times things in H times little G inverse just lands itself back in H. So it's not obvious that these definitions are equivalent, but they are. I'm not going to prove it to you for the sake of time. That's the idea of a normal subgroup. Okay, so here's an example of playing with a normal subgroup. So Z8 plus is abelian. So any subgroup is normal by this note on this slide. So in particular, this 0, 4 subgroup we've already looked at is normal. And we've seen that if you want to now add cosets together, that's kind of a well-behaved thing. It's fine. So like the coset 1, 5 plus the coset 3, 7, what would that be? Well, 1 plus 3 is 4. 1 plus 7 is 8, which is 0. So I get 0, 4. 5 plus 3 is 8, which is 0. 5 plus 7 is 12, which is 4. So when I do all possible sums here, I just get this other coset. So I can just say something like, oh, 1 plus h, that coset, when I add it to 3 plus h, this other coset, I get this coset, 0 plus h, the original subgroup. So all I'm saying is, in this particular example, when I looked at cosets of my subgroup of h, and I tried this kind of like coset combination deal of just like looking at everything in one coset, adding it to everything in the other coset, it all kind of worked out. Like it did what it was supposed to, I think. I mean, 1 plus 3 is 4, and 5 plus 7 is 0, so I should be landing back in the 0 coset when I do this addition. So everything was fine here, and I end up with a factor group of Z4 if I do that. So you could ask, well, like, okay, how could this kind of thing go wrong? Like when I do this coset combination stuff here, how could it not work out the way it worked out right here? So let's just see an example like that. So here's a subgroup H of S3. So remember, S3 consists of all permutations of 3 objects. So like 1, 2, that's a flip of 1 and 2, it leaves 3 alone. 1 goes to 2, which goes to 3, which goes back to 1, so on. We mess with this a lot. So first, I just want to investigate the coset structure of this capital H. So I've written them out for you, but you should confirm that you believe these. So like the identity times H is just H, of course, right? Identity times identity, identity. Identity times 1, 2 is 1, 2. And same thing on the right. The identity doesn't change anything. But now if you form this left coset here, 1, 2, 3 times H. So what you do is you do 1, 2, 3 times the identity, which is 1, 2, 3. Then you do 1, 2, 3 on the left times 1, 2. And then you get the flip 2, 3. So you should confirm that for yourself if you don't believe that. And here's the final coset, 1, 3, 2 left coset. 1, 3, 2 on the left times H. Well, 1, 3, 2 times the identity is 1, 3, 2. 1, 3, 2 times 1, 2, you can believe me, is just 1, 3. So here are the 3 left cosets of S3. Notice S3 only has 6 elements, and I've carved up S3 into the cosets. Every element appears somewhere. If you do the corresponding thing on the right, notice the coset for 1, 2, 3 on the right is different from the one on the left. So instead of having a 2, 3 right here, we have a 1, 3 right there. And the reason is because 1, 2 times 1, 2, 3 in that order. So 1, 2 times 1, 2, 3 is 1, 3. 1, 2, 3 times 1, 2 is 2, 3. So in S3, permutations don't commute in general. And so here you get a left coset and a right coset that are different. And same thing for 1, 3, 2. Its left and right cosets are different. So all I'm saying is here, H is not a normal subgroup. It's not normal because its cosets, left and right, don't agree with each other, as we can see. And so now suppose that I tried to multiply. Suppose I tried to multiply cosets like I did before. So I say, all right, here's a set. I want to combine it with this other set. If I did all possible products, I would do 1, 2, 3 times 1, 3, 2, which is the identity. Then I would do 1, 2, 3 times 1, 3, which you can believe me is, let's see, well, 1 goes to 2. Yeah, okay, gives you 1, 2. Then you can do 2, 3 times 1, 3, 2, which gives you 1, 3. If you do 2, 3 times 1, 3, I get 1, 3, 2. So my only point is that when I try to like combine these two cosets, I don't get another coset. So this set right here, that has size 4, not size 2, it's not one of these cosets I've listed up here. So what's happening is because this subgroup here is not normal, this kind of combination thing doesn't work out nicely like it did before. Now, right, if I try to combine two cosets, I get something bigger. It's not a coset anymore. So multiplication just like breaks down. And another way to see that is like, if this is my subgroup and I want to do the same kind of crushing action I did before with 0 and 4. So suppose you say to me, I want this permutation 1, 2 to be the identity now. That's a restriction I'm imposing, an imposition I'm making. Okay, well, if you insist that the identity and this permutation 1, 2 are the same, then notice if I do this product here, I'm doing like identity times 1, 2, 3 times identity. That shouldn't really change anything. So I should either get back 1, 2, 3 or 2, 3. I should land myself in here. Because if these cosets are keeping track of what's getting glued together. So if 1, 2 and the identity are being glued together, then 1, 2, 3 and 2, 3 should also be being glued together. So anyway, all I'm saying is identity times 1, 2, 3 should basically give me back 1, 2, 3 or something it's glued with. But it doesn't. If you calculate 1, 2 times 1, 2, 3 times 1, 2, you get 1, 3, 2. That's broken, right? Like 1, 2, it shouldn't really change 1, 2, 3. If 1, 2 is acting like an identity, this equation shouldn't be happening, but it is. So the punchline here is that if you want to sort of multiply or combine cosets, that kind of thing only works if the subgroup is normal. So I haven't like fully illustrated to you why that is. I'm just hoping this example kind of fleshes out what could go wrong. And so let me show you a couple more examples. So here's an example where it goes right. So here's another subgroup of the permutation group. So like here, permutations aren't the issue. Like the issue is that H isn't normal. So you can have this kind of coset multiplication work out inside permutation groups. So that's why I'm showing you this. So consider the subgroup here, the identity 1, 2, 3, and its inverse permutation. That's a subgroup of S3. If you compute left and right cosets now, there's only 2 of each, and they're the same now. So notice identity H gives you the original subgroup, and then 1, 2 times H gives you the little flips. That's everything. And same thing over here. Left and right cosets are the same. And so now if you want to like multiply cosets, it works out. So suppose you want to do like this coset times this one. Like what would that mean? You do all possible permutations. So you do like identity times 1, 2. Identity times 1, 3. Identity times 2, 3. That gives you these 3 things, right? But then you would do 1, 2, 3 times 1, 2. Let's see, what's that? So 1 goes to 2, and then 2 goes back to 1. Okay, so 1, 2, 3 times 1, 2 is 2, 3. 1, 2, 3 times 1, 3, what is that? 1 goes to 2, and then 2 doesn't move. So that's 1, 2. And then 1, 2, 3 times 2, 3 is 1, 3. And then finally, if you do 1, 3, 2 times any of these 3 things, you just land back in this set. So here the coset multiplication is like working. You take a coset, you multiply by another one, then you get another coset back. And in fact, you just get 1, 2, H, which makes complete sense because this base subgroup here, that's supposed to be acting like the identity now. Like I'm gluing together 1, 2, 3, 1, 3, 2 with the identity. I'm like crushing these 2 things to the identity. So anything in this set is acting like the identity now. So that subgroup times this coset here, it should give you this original coset back. Identity times anything doesn't change anything. And you can do this yourself if you want to like take everything in H and multiply it by itself. So do like 1, 2 times itself, that gives you the identity. 1, 3 times itself, identity. 2, 3 times itself, the identity. 1, 2 times 1, 3, let's think about that. 1 goes to 2, and then doesn't go anywhere, and then 2 goes to 1, which goes to, okay, so like you would get this one. But basically any combo of these little flips just gives you the identity or one of these 2 things. So 2, 3 times 1, 3, it's going to be one of these 3 things. So it works. All of that to say, for this particular subgroup, it is normal, and if you try to just do this coset combination deal, it's fine. And you'll get, in this case, a group of size 2. There's only 2 cosets, so a group of size 2. You have an identity, and you have a non-identity, and the non-identity times itself is the identity. Right? Non-identity times itself, this is the identity coset now. Okay, so there's some examples of thinking about creating cosets and then combining them. Like, what does that look like? All right, so now I can formally define what a factor group or a quotient group is. If H is a normal subgroup of G, then its factor group, denoted G/H, G divided by H, is the set of either left or right cosets. It doesn't matter because the left and right cosets are the same. So that's the group set. A quotient group is a set of cosets. And then to have a group, you have to like define how multiplication works, and it works like this. The way you multiply 2 cosets is just multiply the 2 group elements and then form that coset. So let me show you some examples of that. So G is now Z9, H is this subgroup. Let's think about G, and the way you say this out loud is G mod H. G mod H. So you don't say quotient group of H and G every single time. Okay, so first of all, note G is abelian, so any subgroup is normal. I don't have to think about normality here. So the cosets are H itself, like 0 plus H, 3 plus H, 3 plus, 0 plus H, 3 plus H, 6 plus H. Those are all H. And then the other cosets are represented by 1, 4, 7. 1 plus H is 1, 1, 4, 7. 4 plus H is also 1, 4, 7. Or 2 plus H. And so if you combine these things, like what would 1 plus H plus itself be? 1 plus H plus 1 plus H? Definition, 1 plus H plus 1 plus H would just be 1 plus 1 plus H. Oh. So 1 plus H plus itself, 1 plus 1 is 2, so 2 plus H. What about 2 plus H plus 2 plus H? Well, by definition, you just do 2 plus 2, which is now 4. But 2 plus 2 being 4, remember 1, 4, and 7 are all the same now. You've glued 1, 4, and 7 together. So 2 plus 2, I mean, it used to be 4 back in Z9. But now you're just living in the coset 1 plus H. So 2 plus 2 is now the coset 1 plus H. Or you could write, if you wanted to, you could write 2 plus 2 is 4 plus H. But you got to know that 4 plus H and 1 plus H are the same set now. And so on. So like, what's H plus H? Well, that's 0 plus H plus 0 plus H. 0 plus 0 is 0. Anyway, that's how you form a table like this. 1 plus H, or sorry, let's do it like this. 2 plus H plus 1 plus H. What is that? Well, you just do 2 plus 1, gives you 3 plus H. But 3 plus H is just the original subgroup. 3 and 0 are glued together now. And if you think hard enough about this, you'll realize, oh, this is just the Cayley table for Z3. If instead of writing an H, I just put 0, like a 0, 1, 2, 1, 2, 0, 2, 0, 1. I've just recreated Z3. I've done it in kind of like a notationally clunky way, but it's fine. So Z3 is a factor group or a quotient group of Z9. And you obtain Z3 from Z9 by insisting that 0, 3, and 6 are all the same now. 0 equals 3. So I should say that this kind of notation stuff, like getting used to it takes a while. Like anything, right? It takes a while to get used to this. But hopefully these examples are, illustrative. What's going on? You have to do this yourself several times, though. So here are some exercises to try. I'll give you some guidance on this first one, but just try them. Okay, what are we going to do? We're going to think about a quotient group of D4. These are symmetries of a square. There's 8 of those. There's 4 rotations, 4 reflections. Let R denote the rotation by 90. So I want you to verify that this subgroup is normal and then think about what D4 mod H is. So if you insist now that rotation by 0 and rotation by 180 are the same thing, what consequences does that have? What do the cosets look like? And so on. And then here, U8, 1, 3, 5, 7, these are the multiplicatively invertible elements of Z8. It's a group under multiplication. So I want you to verify that the set consisting of just 1 and 3 is a normal subgroup, and then think about what this quotient group looks like. Okay, let me give you some brief guidance on this first one. For the second one, notice, by the way, U8, this is just regular multiplication, so the group is abelian. So when I say verify a subgroup is normal, in that case, all you got to do is say group is abelian. So I don't have to verify anything, really. But for this first exercise, these symmetries, they don't commute with each other in general, so you have to actually verify. Okay, so here's some guidance on that first one. So first you have to recall what D4 looks like. 4 reflections, 4 rotations. Here are the 4 rotations. Here are the 4 reflections. So you should, I suppose, just remember that there's kind of this one base reflection, and then reflection times rotation another rotation. Those give you all 4 reflections if you do that. And in D4, we have this formula from chapter whatever it was, that you can scoot an S past a rotation if you want to, but it costs you a possible power change up here. So to verify the subgroup is normal, the subgroup consisting of just doing nothing, doing rotation by 180, I mean, the easiest way to do it is just to look at the left and right cosets and see that they line up. So if I do nothing and I multiply that times my subgroup elements, like do nothing times do nothing is do nothing times r squared is r squared, and that's true whether I'm doing nothing on the left or right. So there's my original subgroup as a left and right coset. Now let's think about RH. What does that look like? Well, do r times nothing, you get r. R times r squared gives you r cubed. If you do it on the right, so if you do nothing times r, you get r. If you rotate by 180 and then rotate by 90, you get 270, r cubed. So RH and HR are the same. So now let's pick some other group element. I picked S. Notice we haven't dealt with a reflection yet. So if you do S times the subgroup, well, S times do nothing is S. S times r squared is SR squared. Okay, what about on the right? So if you do nothing followed by S, you get S. If you do r squared followed by S, you get r squared S. But this formula here lets you just scoot that S right over. You get SR squared, and so now notice these two cosets line up with each other. Finally, notice we don't have a coset with either SR or SR cubed in it, and so we could actually quit here. We could say, well, I've looked at 3 cosets so far. There's only 2 group elements left. The only thing we haven't seen yet is SR and SR cubed. Those must constitute the final coset. So you would kind of get for free that this last line is equal, but if you want to see it written out, here it is. SR times nothing, do nothing is SR. SR times another r squared is now S with 3 r's. If you do it on the right, do nothing times SR is SR. R squared times SR is r squared SR. And then let's see, what did I do here? Okay. There's probably a more efficient way to do this, but I shifted the r over. So this is like an r to the 1. And when I do that, I pick up an r cubed. So if I scoot the r over, I now have an r squared and r cubed, which is 5 r's. That's rotating by 90 degrees 5 times. That's the same thing as rotating by 90 degrees. So it's the same thing as doing rs, and rs is the same thing as SR cubed. And so this right coset consists of SR and SR cubed, and you get a match. So the subgroup is normal. Every left coset equals every right coset, and to see that, you do have to remember this formula, but it works out. And so now if you want to build a Cayley table, you have to think about, how do I multiply like these 4 things? You don't have to think about right cosets because they're identical to the left ones. So think about, how do I multiply these 4 things? And so one way you could think about it is just definitionally. So where's my definition? It says if you want to multiply 2 cosets, just multiply the 2 group elements here and see what coset you get off of them. So like RH times SH, just multiply the 2 group elements, RS. Okay, well, what is RS? It's not on my list up here, so I'll make it appear on my list. So RS by this formula is the same thing as SR cubed. SR cubed is in this coset here. So SR cubed and SR are like the same thing now. So I get the coset SRH. So all that to say, this coset times this one, little RH times little SH, if you multiply those 2 things, definitionally, you just get SRH. So if you're building a Cayley table, your RH row and your SH column would meet at SRH. And of course, if you wanted to see this another way, like this multiplication is just saying, take everything in RH and multiply on the right by everything in SH, form all possible pairs. So you could do R, S, R cubed, S, R, SR squared. R cubed, SR squared. Do all those possible products and see what you get. So R times S is RS, of course, which is SR cubed, because my formula here. R times SR squared is RSR squared, and then you can shift what did I do? I shifted the S to the left, cost me an R cubed. So this is SR to the 5th, which is SR. And then R cubed S, you can just shift the S over and you get SR. And then R cubed SR squared, same deal. Like you shift this over, you get, anyway. If you form all possible pairs of products of this coset stuff on the left and this one on the right when you form the products, respecting that's on the left and that's on the right, what do you get out of that? In the end, you get an SR cubed, you get an SR, you get another SR, you get another SR cubed. You land yourself right here. So whether you think about it just from the definition or whether you think about it this way, you're going to get the same thing. And the fact that H is normal is what guarantees this works out. So I haven't proven this to you formally, but I'm just sort of telling you that if a subgroup is normal, then this kind of multiplication works just fine. But if your subgroup is not normal, we get this kind of nonsense, where you try to multiply two cosets, and now suddenly you've left the land of cosets. So the technical term is multiplication is not well defined. So if you multiply two cosets, you're supposed to get another coset. You got to stay. You need like a closure property, if you like, right? You got to stay within the universe. This example here shows that sometimes when you multiply cosets, you leave the universe of cosets. That's bad. You don't want to do that. Whereas here, what I'm saying is if you do R times S, that's basically now SR. So I guess one last comment here as a natural consequence, like suppose I told you, hey, rotating by nothing and rotating by 180 degrees, those are the same now. What consequence would that have for the rest of the group? Well, as a consequence, rotating by 90 and rotating by 270 must also be the same now, because 270 is 180 plus 90. And it turns out that this reflection and this reflection times R squared, those must also be the same now. Why? Because R squared and doing nothing are the same. So when you write S and SR squared, those better be the same thing now, if R squared is now the same as doing nothing. So there's kind of like a natural carving up of the group into things that get glued together. And because the original subgroup was normal, multiplication still translates. It works fine. Okay, so that's the idea of factor group and normal subgroups. So to form a factor group, you need a normal subgroup first, and then you can combine cosets in the way I've shown you. So I would finish this by building a Cayley table for this. So like it's going to be a 4x4 table. Here are the four cosets. We know one of the products, RH and SH, is, what do we get? Oh, SRH, right? Got this. This is still the identity. So this times anything would not change. So this R naught, R0H times RH should be RH. Things like that. You can fill in the rest of the table. And then for this one, we've already talked about that H is normal. So here I just want to leave it to you. Like the cosets of H, 1 and 3 are the same now. This group's not very big, it only has size 4. So if you identify 1 and 3, surely you also have to identify 5 and 7 because cosets have to have the same size. And then just think about what table you get. You get a 2x2 table. Okay, so hopefully all of this was clear. If anything is not clear, please contact me. I'll still be in email touch while I'm gone. So feel free to shoot me an email. Otherwise, we'll discuss any questions you have when I get back.